We're going to talk about using LLMs to adjudicate static analysis results or alerts. Software vulnerabilities are a serious concern for the DoD. We know this audience is not only DoD, so we recognize that vulnerabilities are a serious concern for industry and beyond as well. We're going to use some names of some processes that are specific to the DoD, but you'll recognize that there are similarities to software security just generally. The software may have known or unknown vulnerabilities. There are many known vulnerabilities in software, some in third-party packages. There are about 241,000 currently published CVEs. And code flaws can lead to vulnerabilities. There are flaw taxonomies, such as CWEs, or common weaknesses and exposures, or common weakness enumeration, and certain coding rules, and many more. Before software is fielded in the DoD, the authorization to operate, or ATO process, assesses risks that the software may introduce. During test and evaluation done by the development org, and independent verification and validation done by an independent team, software analysts evaluate source code for security weaknesses to measure risk and enable code improvement in preparation of the ATO and fielding. During the T&E and IV&V processes, there are many types of testing. In this presentation, we'll focus on static analysis. The software analysts use static analysis as a standard method to evaluate the source code, but it requires significant manual effort and is inherently difficult, time-consuming, and expensive. The volume of findings or static analysis alerts is often too large to review entirely, causing programs to accept unknown risk. And when they do that, we end up with fielded software with many code flaws and vulnerabilities. We address the problem with an LLM-based tool for use in T&E and IV&V, with a goal that our tool will automatically adjudicate a large percent of alerts with high accuracy, enabling more complete adjudication, thereby reducing unknown risk and enabling the DoD to remove vulns before the software is fielded. The recent research shows LLMs work well in code analysis tasks, although challenges remain. So, one set of researchers found GPT works well for use before initialization for adjudicating use before initialization alerts. Another set of researchers used LLMs to detect code flaws in code being edited, and that reduced the rate of code flaws by 90%. And another set of researchers report success using LLMs to generate formal verification proofs, beating state-of-the-art formal verification tools on a number of hard cases. Today, analysts typically manually adjudicate only the highest prioritized alerts, leaving the problem we talked about, remaining code flaws and vulns. So LLMs are a significant breakthrough for code analysis. Older ML techniques lack interpretability. They don't provide an explanation, and they often pivoted on irrelevant details that simply happen to correlate with code flaws in the training data sets. LLMs, on the other hand, produce a detailed explanation to support their final adjudication, and that explanation can be manually verified by experts. GPT-4 has demonstrated an ability to correct its own mistakes when asked to double check its work. An LLM-based tool can handle even alerts whose adjudication requires analyzing multiple functions spread across the code base. To do this, our tool will use the LLM itself to generate function summaries, function preconditions, and other intermediate results that can be combined for a final answer. In our preliminary work that we're presenting here, we've used GPT-4. GPT-4, however, is only available as a web service, and it can't handle DoD, CUI, or controlled unclassified information of certain levels, or classified code. Similarly, in non-DoD uses, there are other reasons to not want to submit code to a web service. A competitive alternative LLM is Llama 3, which is open weight, and it can be downloaded and run on premises. It's available in various sizes. The larger sizes require high RAM GPUs, which require an investment. So the LLM, or LLM-based tool, ingests static analysis alerts and source code, and outputs adjudicated true positives with a trace, adjudicated false positives with a proof sketch, or an adjudication of uncertain. In the simplest case, the tool creates a query or a prompt to the LLM for each static analysis alert. The prompt includes the static analysis alert, the source code for the relevant function, and instructions what to do, and the output from the LLM then has its final answer in easily parsed JSON. The next slide gives an example of this simple case.
Okay, so this is an example of GPT-4 adjudicating an integer overflow in the Linux kernel. So let's see, can I point here? I think I can, right. So you can see here, there's a line marked alert 1. What we do is we take the source code, we add comments onto the lines that the static analysis alert is about. So this line, you can see there is an addition, and the alert here is that that addition might experience integer overflow. And then on the next line, there's a further alert that there might be a buffer overflow here, meaning that this memory copy would copy data outside the range of the buffer. So we give this to this is the exact prompt that we gave GPT-4, except the ellipses indicate code that we've omitted just so that it fits on the slide. And then at the end, we ask it to give its answer in JSON, which GPT-4 actually works very well at. And right, so what does it do? Well, first, let me actually just point out one thing that's might be a little bit unusual here. In here, the integer overflow, it overflows, you get a small number. You take this very large number, add 2, you get a small number. And then how that leads to overflow is that over here, you subtract that number. So instead of subtracting a large number, you subtract a small number, and that leaves you with a large number, which is then the amount of data to copy. So what does GPT-4 do in this case? Well, it actually explains its reasoning. On this line that defines copy line, it says, oh, this MB SSID subscript 1, if that is equal to 255, then this arithmetic here will overflow because it's only an 8-bit integer. Then it looks at the relation between the size of the allocated buffer compared to the size of the data that's being copied into the buffer. So it determines that a large value, if MB SSID subscript 1, if that is large, then that should and does result in a small allocated buffer, and that it should but doesn't results in a small amount of data being copied into the buffer. Instead, due to that integer overflow, you actually copy a large amount of data into that small buffer, which overflows it. Then at the end of its response, GPT-4 gives us its final answer in the format that we requested. We've also tried this example on the patched version of this code. In the patched version, the size of the integer is increased to size t, and in that case, GPT-4 correctly tells us that there is no longer any integer overflow or buffer overflow. And I guess these links are kind of small, but if you are interested in the slides, you can email us, email address on the last slide, and we can send you them if you're interested in these links. Okay, so large language models have a context window, which is the maximum size of input plus output. Usually, the context window can fit a single function, it can fit several functions, but it cannot fit an entire large code base. Now, more recent LLMs have pretty large context windows, but there's still an issue in that if you fill out the entire context window, the LLM generally performs a bit worse than if you only fill out like the initial part of it. So even if you can fit everything in the context window, the LLM usually works a bit better if you only have a small amount of data. So in some cases, the LLM can make its adjudication based only on the function that contains the flagged line of code. In that case, great. In other cases, we need to summarize the rest of the relevant code base so that it can all fit in the context window. So there's a few strategies that have been documented about this. One way that you can do this is to use traditional static analysis to find the needed data. Another thing that you could do is to use the LLM to generate function summaries. We've also looked at a few other options. One option is to just ask the LLM to ask us to give it the information that it needs. For example, if it needs type definitions, if it needs the definitions of functions that are called from within the function that it's analyzing. So we can give it a few options that it can ask us about, and then we can supply that information. And it's not like us personally doing this, we would have some tool that would do that. Another option is to have the LLM generate preconditions to avoid the bad state that's being warned about. And then what we can do is we can have a tool that analyzes the callers of that function and then see if the callers satisfy that precondition. And I'm going to talk about this bullet point more on the next slide. So here's what that strategy looks like. So we have a top-level tool. Let's say that we want to analyze, that we want to adjudicate an alert in this function foo. So we go and ask the LLM, we give it this function foo and ask it to generate a precondition for avoiding the flagged buffer overflow. And then the LLM comes back and says, well, the precondition is that sterling of username must be less than or equal to 52. Then our tool takes that, it looks at the callers of this function foo, it says, oh, there's this function bar that calls foo, and then what it does is it takes this precondition that the LLM previously generated and then adds that to a new prompt, gives it this function foo and asks this function, this function bar, and then we ask the LLM, does this function bar, does it satisfy the precondition that it previously discovered? Okay, and then in this case, the LLM comes back and says, no, it doesn't satisfy it, and it gives us a trace showing that the precondition is falsified. Then what we do is we just combine the justification from these two different LLM responses, and then we can give that as our final answer with the adjudication that it's a true positive. Okay, so LLMs sometimes make mistakes. And in general, LLMs are non-deterministic, so if you give it the same exact prompt, it can give you different answers different times. So one thing you could do is maybe ask it 10 times or 100 times the same prompt, and then if it always gives you back consistent answers, then you can assign a higher probability to it being correct than if it gave you inconsistent answers. Another thing that you could do is you could ask the LLM to double-check its own work. And we've tried that, and it actually works pretty well in the cases that we've tried. So there's one example program that we asked it to adjudicate a use after free alert. And in that case, it initially gave us the wrong answer. We asked it to double-check its work, and then and when we ask it to double check its own work, it says, oh, this use after free scenario actually doesn't occur because the program uses stirdup to duplicate the string. So it's not actually used after it's being freed because you make a duplicate of it that you don't free. Now what happens if we delete that stirdup call? In that case, there is a real use after free bug. And in that case, when we ask it to double check its own work, it confirms its previous answer, says, yes, there really is this use after free bug. So why does this technique work? Well, I mean, of course, it might work in some cases just for the same reason why it works with people, but there's also another reason why it might work particularly well with LLMs. So LLMs training data comes mostly from text that people post on the internet. So if someone is like writing something that they're going to post, and then they realize halfway through that they've made a mistake, they generally delete what they've written and rewrite it so that it's correct. They don't like post this partially incorrect thing and then post a correction. So the LLM might be trained that it's, even if it kind of realizes that it's incorrect, it might just keep on going because there's really no cases of people posting text on the internet where they realized halfway through that they got it wrong. But there is a lot of cases on the internet where other people critique posts written by other people. There's a real lot of those cases. So that's why the LLM might work better, because when it's asking to double check its own work, it's not necessarily making a distinction between this is its own answer versus someone else's answer. So it can just look at this answer and see if it's correct or not. And then there's a lot of examples of that on the internet in its training data. So that, and of course, that's just speculation on my part. I don't have a real answer, but it seems like it's pretty reasonable possibility. Okay, so in some cases, in order to adjudicate a buffer overflow alert, you need to be able to identify a loop invariant. So for example, in this code base, or in this code snippet, there's an array axis in the middle of the loop, and in order to determine whether that array index is always within bounds, you need to have a loop invariant about low and high, and mid is just the average of low and high. So what does GPT-4 do in this case? Well, we prompt it to, we give it a hint that it's supposed to find a loop invariant, and in that case, first, as a precondition, it tells us the precondition here is kind of obvious, just that n should be the size of the array, and also n should be non-negative. And then more interestingly, GPT-4 steps through this code. It finds a loop invariant. 0 is less than or equal to low, is less than or equal to high, which is strictly less than n. And then it sketches a proof of that loop invariant. And then it uses the loop invariant to show that these array axes are always within bounds. Now, in this example, this proof sketch is informal. You kind of a human being look at it and give it a thumbs up or a thumbs down. But another interesting possibility is to have the LLM actually produce a formal proof of the loop invariant. And there are tools that can check formal proofs like that. For example, Pharmacy can be used to check mostly handwritten proofs, but it could also check a GPT-written proof. So we've tried this just on a very simple example here. This is just picking a random element, a random value in an array. Unfortunately, GPT-4 actually gets it wrong the first time we ask it. It gives us this, which is not a valid precondition, but what we've tried then is just copying the error message that Pharmacy gives us and then just pasting that at GPT-4. And giving that error message, GPT-4 actually gives us a correct precondition. So in summary, it seems like there's maybe some potential for GPT-4 to do this. It's not at that stage yet where it can give us good answers, but maybe with some fine-tuning, in the future, this might be a viable path. In interest of time, I think I'm going to skip this slide. It's basically just looking at multiple bugs, and it eventually gets the right answer. And I'm going to hand it back to Lori.
So given that automated program repair, or APR, eliminates the need to adjudicate some alerts, our methods can be used can be targeted at particular types of code flaws. The list on the bottom of the slide is of just 10 of the APR tools and of the CWEs that APR tools and techniques exist for C and C++ tools. David Svoboda presented here yesterday about about his research on APR that currently works for 3 types of code flaws. We want to target our project work to prioritize types of code flaws that are of interest to this community. So we would appreciate your input about what CWEs you would like us to prioritize in this work. Perhaps you'd like us to prioritize CWEs that APR tools don't fix yet, or perhaps your organization still needs to adjudicate alerts like that. Perhaps you're interested in true positives being adjudicated because you want to use them for offensive operations or other reasons. So at the breaks or afterwards, contacting us by email, we would appreciate your input. So far, our progress is that we've developed some scripts. We've done some initial experiments with GPT, some of which have been shown in today's presentation. We've published a Crosstalk journal article, which includes more of the experiments and results. And then we have plans for further R&D. This project continues through the end, actually through October 1st, 2026. We're looking for collaborators. As a collaborator, your organization would test our tool on code that you're working with in your own environment. As an FFRDC, specific to the DoD or other government organizations, SCI can rapidly iterate with DoD users based on their feedback. We're also interested in collaborators from industry. Your organization could potentially better secure your code without spending more money while contributing to advancing the research field as collaborators. So at the bottom of the slide, there's a link to the article that we published, and Will's contact info is on this slide. So that concludes our presentation, and we would welcome questions.
So I see here it says you could potentially be more secure without spending more money. The first question I have is actually about maybe on the roadmap on the left with respect to on-prem LLM. So if it's not on-prem, I'm going to be spending money, aren't I? I wanted to know, if I collaborate with you, do you give me a ChatGPT license and do you let me run queries against it with your account, or am I spending that money?
At this point, we would not. We don't have plans to cover GPT licenses. As an FFRDC, one of our priorities involves being able to show impact on the DoD. So for DoD organizations, we're considering possibly providing some on-prem equipment as needed, but that's not a for sure yet either. So
I see it's on the roadmap to show me how to host it myself. I think that would be for me, that would be great. If you could teach me how to host it all myself and I could run it all myself, I think if that as a priority, that would really help me help you.
Absolutely, that makes sense.
One more if I can. Does it produce fixes in the pull request? How does it offer me to fix my code? Or does it just rewrite my code to make me do the pull request?
Right, so I guess we haven't focused too much on that, but there is some examples where it just, just unsolicited, it offered you a repair. So for example, it said, in here, you need to insert this code at this part of the code. You need to insert this snippet, so you check to see if this variable is null or not.
Gotcha, so it's like a report, and then I implement whatever the advice is.
Yes, and I guess if you want it to automatically repair the code, we could also automate that pretty easily.
It's a bit of a tangent. Are you guys actually planning on diving down the rabbit hole of self-repairing answers for LLMs? Are you planning on pursuing that at all as maybe either a parallel or an independent, I guess, sort of solution? What are your plans as far as implementing sort of like self-learning when it comes to that?
Yes, that's an interesting question. And I guess one thing that we could do is like, for this pharmacy example, you can see how it gave a wrong answer, but then we give it the error message, it gives us the right answer. So what we could do in this case is basically do that a bunch of times, and then we can get training data and then fine tune it so that when we give us this code, rather than needing to go to the error messages, it could just jump right to the correct answer. So that is something that we are looking into. And that is a very interesting, and we hope that'll work. That'll make this pharmacy stuff work a lot better.